Good evening once again. This is MP Live Lessons, and we are back with computer science once again. But this time it's paper 2. So this is the paper that you'll have slightly less time on for 90 marks. So this is 90 marks, as I said. And within these 90 marks, you'll be covering the following topics, and this paper would be 1 hour and 45 minutes long, which is slightly less than the 2 hours that you get for the programming paper. Now, based on the exam information, the advanced information, one of the topics we start often with are the number bases. Now, first of all, as basic, you need to know what's meant by denary system, binary, and hexadecimal. Now, denary is what we use in normal life, so base 10. So like 10 digits. So like 0 to 9. And we likely use this now today because we have 10 fingers. Whereas binary is base 2 and has 2 digits. On the left you can see there's 0 and 1 because there are 2 states, if you like, for electricity. Because many things in your computer are made up of switches and they can be turned on or off, in a simple way to put it. Hexadecimal is base 16, and we'll use 16 digits, so it includes 0 to 9, but goes even further. It goes to F. Now think about why some of these might be used more than others. Hexadecimal may be used more than, let's say, binary because these are often used for codes, like for example for errors. This is because they have fewer characters to store the same number. And this makes them easier to read. And whereas if you used binary, that wouldn't be a good idea for, let's say, error codes, because if you don't type the error code correctly, if you mistype a 0 for a 1, it changes the error code dramatically. Now, what's going on? Now we have some bases to convert with. Now, in the exam, you could be asked to convert from any base in any direction. For example, decimal to binary, binary to decimal, binary to hexadecimal, and the other way around, or even decimal to hexadecimal. First, you need to know about the number systems of each. So denary is base 10, and with the digits, for example, the units column of times 1 times 10, like your tens column times 100 times 1,000, and so on. And what's happening really is you'd start at your base number, 10 to the power of 0. This is your first digit. For example, if I put just 5 here, that's just 5, because anything to the power of 0 is 1, if you know from maths. The next column to the left is 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. For example, if in denary, if I write 420, what I'm really writing out is 4 times 10 to the 3 plus 2 times 10 to the 2, actually, wrong powers, 4 times 10 to the 2 plus 2 times 10 to the 1, and nothing times 10 to the 0. So really that's splitting it up, 400 plus 20, and that's it. Now the other number systems like hexadecimal and binary just work in the same way, except they just use a different base. For binary, for example, we start with times 1 in the rightmost column because 2 to the power of 0. Next digit will be multiplied by 2, then by 4, then by 8, then by 16, then by 32, then by 64, then by 128. And that's all you really need to be familiar with GCSE. So for example, if you're converting from binary to denary, what you do is you see if, for example, if there's a 1 in the column, you'll take the number and you'll add it onto your total. So for example, if I have the pattern 1 0 0 1 1 0 0 1, you'd add up all the numbers in this column here that have a 1. So this would be 128 plus 16 plus 8 plus 1, which in the end gets you 153. Remember, you are not allowed a calculator in the computer science exam. Whereas going from decimal to binary, you'd sort of do the opposite. Let's say you have the number 185 and you want to convert it to binary. Now if I rub out our little table again, what we first do is we take the largest number we see in the table, we put a 1 in its column, like 128 is the largest number that will fit into this 185, and then we take it away. If it doesn't fit into, let's say, the next largest column, like 64, 57 can't fit into this times 64 column, we'll put a 0. But it can fit into this 32, so we'll put a 1 and take it away from this number. And fit in this 16. They can fit into this 8. And it'll just fit into this 1, we'll put the zeros here. Now that's the bits pattern to represent the decimal number 185. Now, hexadecimal works in a similar way again. So at the right, your first column is just 1, which is 16 to the power of 0. Your next column is multiplied by 16, because it's 16 to the power of 1. Your next column is multiplied by 16 to the power of 2. This would be 256. And very rarely you'll be asked to have a fourth column, 16 to the power of 3, and that's multiplied by 4096. For example, you will have digits from 0 to F, and just a reminder that A, B, C, D, E, and F are just extensions of these numbers. So A would be 10, B would be 11, C would be 12, D would be 13, E would be 14, and F would be 15. The method that we use to convert decimal to binary is quite similar to convert from decimal to hexadecimal. For example, if we use the same number 185 again, this time we'll need to almost divide it by 16 first. So we only want these two digits here. This will be represented by a 2-digit hexagonal number. So if we write out the multiples of 16, you could just try an error, almost. So as we can see, the largest multiple of 16 that goes into 185 is 176. So we'll take that away first. Now, 176 is equal to 16 times 11, or 16 to the power of 1 times 11. However, 11 is not a single digit or character. So this is just the letter B. And since we have 9 at the end, 9 is just a number, so we put 9 here. And going the other way, from hexadecimal to decimal, we just use this table and see whatever digit is in there and multiply by the thing above it. Like on the rightmost column, like your units is just 1, then the next column to the left is 16, then 256 for the next one to the left, the third one from the right, almost. And then the far left column, if there's a 4-digit number, is 4096. That's what you multiply by. Now, hexadecimal and binary are actually quite easy to convert to each other. Now, hexadecimal to binary, there is a bit of a trick, because each hexadecimal digit can be represented as 4-bit digits. And remember, 4 bits is just 4 binary digits. So what you do is you, for example, B9, if you want to convert this to binary, you convert each hexadecimal digit into decimal perhaps, and then convert that into binary. So for example, B equals 11. That equals, if we use just this bit of our table to convert, we get 1, 0, 1, 1. Because 8 plus 2 plus 1 is 11. So that's our first bit. And 9 is just a normal number. And we can convert this into binary, which is 1, 0, 1, 1. Now what we do is we just put these together. So B9 in binary is 1011 1001. Going the other way from binary to hexadecimal, we could use the same trick again. Starting from the right, we split our bit pattern or binary digits into chunks of 4. So for example, if we've got this, we split them into 2 chunks here of 4 bits each. Then we find its numeric value in decimal perhaps. So on the right we've got, using our table, we've got 8 here plus the 4 here. We ignore the 2 because it has a 0 and then a 1 at the end, so that's 13. Now 13 isn't a digit, so we have to convert it to one of the letters, and if we use our table, this just becomes D. Whereas on the left, if we use the same table just for the 4 bits, that's just 8. So this binary pattern becomes the hexadecimal number 8D. The next thing you may be expected to know is binary arithmetic. For example, this can be a simple 2-mark question. Add the following binary bit patterns. Now you only need to know a few rules. If you have 2 zeros, just a 0 plus a 0, like how you'd normally add in column addition, this just becomes 0. If it's 1 plus a 0, or a 0 plus 1, this just becomes 1. However, if you have two ones, you write 0, but you carry this on to the next column. And finally, the last rule is, if you have 1 plus 1 plus 1 like this, you do 1, carry another 1 to the next column. Otherwise, for every 2 digits of 1 seen, carry an extra 1. For example, in the first column we've got 0 plus 1 plus 0. 0 plus 1 is 1. 1 plus 0 just gets us 1. Same again in the next column. Now we got 1 plus 0, which is 1. Then add another 1, so 1 plus 1. We write as 0, and we carry a 1 to the next column. Now we've got 3 ones, so you write down another 1 and carry 1 to the next column. We've got 3 ones again, 1 here, 2 and 3. So that's 1, carry 1. We've got 3 ones again, so 1, carry 1. 3 ones again, 1, carry 1. 3 ones again, so 1, carry 1. And there's nothing here, so that's just 1 at the end. That's what you get after you add these numbers. Next, we move on to representing sound. Now, firstly, why does sound need to be converted into binary or a bit pattern? This can be a common exam question. So from what we know, sound is an analog pattern. And what this means is you can have varying levels in between. It's the top of the peak, down the peak. It can be measured in a variety of different ways to, like, for example, the nearest, um, let's say, thousandth. Whereas, um, computers only understand binary. which is basically digital. Another good way of thinking is, for example, with an analog controller, you can slightly push, let's say, a joystick forward, and that will be represented in the game. For example, let's say with a player walking forward slowly. Whereas with a digital controller or digital joystick, even whether you push it forward fully or just a tiny bit, it's the same amount of force. For example, no matter what you do, they'll walk at the same speed. A character may walk at the same speed. So analog, you've got like various levels in between, whereas digital, it's just one or the other. Now, by sampling, what we mean is we sample the sound, we measure its um, depth, for example, like it's part of the wave. For example, if a computer can sample sound, let's say 4,000 times a second, for example, it could represent my voice 4,000 times a second, it will interpret it 4,000 times a second, and then it will understand it, it will interpret the sound, then whether store it or broadcast it or put it into more speakers. Now, the formula for file size depends on the sampling frequency. So this is how many times per second the sound wave is sampled, or the wave is interpreted, like its amplitude or frequency. This is often given in hertz because it just means how many times per second. Then we multiply this by the bit depth. So like the number of bits we're given to represent the sound. For example, if you have more bits, the file size will be bigger, but the sound file will sound much better or more closer to an original because it can measure much more in between, if you like. And then lastly, you multiply this by the duration, like for how long the recording is, which is in seconds. Now, how does increasing the quality of the sound of the file size increase the size? Now, what can be increased? You can increase two things: the bits depth or the sampling frequency. We can exaggerate this by demonstrating on this little sound pattern. Now, the bit depth is where we almost round the wave up. We have to force it into some level in binary. For example, if we use 2 bits, we can have 4 possible values. If we have used 3 bits, we have 8 possible values, because we can store 8 values, like 0 to 8. For example, down here would be 0, and this could be like some other number like 8. So we could have so many in between. What happens is, every so often along this, which is basically time, this wave gets sampled, so the line will be taken and it will be rounded off nearest to the nearest point, like this. it gets close, but it isn't fully accurate. It isn't as smooth, if you like. And that's why you can have obvious auto-tunes where the change in pitch, for example, is quite obvious. It goes in steps rather than as one smooth change. Next is representing images. Now, what is meant by a pixel? So a pixel is a picture element. So this is often a very small square in a big image that will contain a color represented by a bit pattern. Now, color bit depth tells us how many colors are possible to be stored. For example, if we use, let's say, a bit depth of 2, this is very similar. We can store 4 colors. If we do a bit depth of 3, we can store 8 colors. For example, if I list out all the possible bit combinations, that's how they can represent those different colors. They can be any color you like, really, but usually the hex numbers, for example, will store these colors as well. And remember, hex can be easily converted to binary. For example, with the color bit depth of 2, we have 4 possible bits patterns, so like 0, 0, 0, 1, 1, 0, and 1, 1. Whereas with 3 bits, we have 8 different combinations. And this increases exponentially. For example, if you use 4 bits, we could store 16 colors. So basically 2 to the power of bit depth gives us how many colors we could store. That's as the maximum. Similarly, the file size is very similar to the SAN representation. It's also the bit depth, but this time we multiplied this by the number of pixels. And basically the number of pixels is also the length of image times the width. Next, we move on to a bit of compression. Now, we could have very large file sizes, and there's a few ways we could compress them to make them smaller. One way to do this is run length encoding. Now, before we start this algorithm or way of compressing, so compression, this is a lossless method of compression. This means the original quality can be restored. And the way to do this, for example, if we have this bit pattern, which could represent things like images, it could represent sound, it could represent data, for example. Now, what's the file size right now? We just count the number of bits here, or binary digits. I'll split them up into 4s here. So there's 20 bits right now. How does run length encoding make it smaller? So what run length encoding does, it compresses repeated digits into what the digit is, and how many times it appears. For example, if we do run length encoding on this, we'll follow this little format. So we'll say first what the digit is and how many times it repeated or shown. This single 0 becomes 0 and just a 1. This little pair, it'll be a 1 here. That appears twice, so a 2. Single 0 on its own, 0, 1. Then a 1 on its own, 1, 1. Then 2 zeros would be 0, and that appears twice, or 2. Now we got 5 ones, and that is simply a 1 repeated 5 times. Then we got a single 0, single 1. Now we got 5 zeros, and there's a single 1 at the end. Now if we add more repeating bits, and there's fewer single or double repeating bits, the file size would even be smaller. And that's the advantage with the run encoding. So if you have many repeating bits, you can simply compress them down a lot more. Next is character encoding. So this is more useful, let's say, for text or text documents. Again, character encoding is what we call a lossless form of compression. This is where we can restore the original quality. Now, usually letters or characters, including spaces, aren't binary digits, but we represent them by using ASCII usually, which has 7 bits per character. Now, ASCII stands for or uses the American English characters. So it's like A to Z, like lowercase and uppercase, a few common punctuation like commas, full stops, even spaces count as characters. Now, Unicode is 16 bits per character. However, this can include other languages. Because you've got 2 to the 16 different characters you could store. Which is a lot more. Whereas with ASCII is just 2 to the power 7, which is just 128. And for example, you can give each of these characters a decimal number as well, based on the binary digits they are represented with. For example, I think a capital A or lowercase a was represented by 65, and then it follows a regular pattern. The next character in the alphabet would be like this, so 66. C would be 67. This would be like lowercase, I think. D 68, E 69, and so on. So this follows a pattern. Now, with Unicode, it does use the same numbers for the new alphabet characters. For example, A, B, C, D, E, it still follows the same bit numbers. Like 65 is still A in Unicode and so on. Now, why one might be used over the other? For example, if you're in France, you would likely use Unicode because it has characters that aren't found in ASCII. If you're just in, let's say, the UK or America, you would likely use ASCII in your computers because one, it can save much more space because you're using fewer bits per character, and two, you just don't need many of the Unicode characters. Now, one way to do this character encoding is Huffman coding. Again, a lossless type of compression where we can restore the compressed package into its original text. For example, if we have this string, when we ignore the speech marks and we include the spaces, how many bits are used to represent this if we use ASCII? So in total there are 24 characters. So times 7, this gives us 168 bits. Now, we're going to use Huffman coding to try and beat this. So try and reduce this file size to its for this speech. Now, what we do is use a Huffman coding tree. So if I have the text here again, now we have a table and the frequency. You may not be asked to draw a Huffman coding tree in your exam, but you could. Usually you'll be asked to interpret one. Now, the way we build it is we start with the bottom two here, and we combine them to make a little larger, like block. So we'll combine them together. And then we'll put them again in the list as if it was like any other character that had 2, like a frequency of 2. And remember, we put this frequency in descending order. Remember, we put these little lines underwards under this small block. We'll cross this off. We'll call this little bit 2A. Next, you'll then combine these and put them in similarly somewhere else. Then we put these together. Then, for example, we could put these two together now, since these would all be here. So you group these again into another tree of its own. We'll just tick off all the characters we've done. Now we combine 2C, A, I'm just using letters here to distinguish each common or similar tree. Now I can combine these two lots of 3. And we keep just doing this until we get a really large tree with the one thing at the top. Then we combine the two 4s together. If we combine these two 5s together, why does it keep going off? Then the 6 and the 8 combine together to make a 14. Branch this, and then combines ultimately to a 10, which gets you 24 characters. Tells you how they split. Now each time it goes to the left, it's a 0. This is a bit of a mess. Each time it goes to the right, it's a 1. So you almost follow the tree down until you get to the character you want. And what this does is, it puts the characters that are more frequently used at the top, and they'll have shorter bit lengths. Whereas the ones that are less used, they're more towards the bottom, but they have larger ones. Now, if I draw the bit patterns to get each character, for example, the space, is you go down the left once for the first time, so that's 0, then 1, so that's just 2 bits you need. N is also 2 bits because you have a 0, 0. Now if we go to try and find E, you go to the right, you go to the right, then right again, then left. So your bits pattern will be 110. So that's 3 bits. O, you follow a similar pattern, and that's 111 instead. So that's 3 bits. To get A, character A, you go so to the right, 1, left, 0, left again, 0, then left. So 1, 2, 3, 4, that's 4 bits. To get the character R, you'll need 5 bits. Same for U. To get the character C, 1, 2, 3, 4, 5. Same with the J also. And all these happen to be just less than the 7 bits usually used, each for ASCII. To get I, we go 3, 4, 5. So 5 as well. So using Huffman coding, there are, if you multiply the frequency times the number of bits you need to represent the character, so that's, if we use a different color, 10, 10, 9. If you do a bit of maths, thirty, 40, 50. We use 76 bits, so we save about 92 bits compared to ASCII. The problem is with this Huffman coding tree is it depends on how many times each character appears. Now, characters may not always appear frequently, like more than others. If they appear the same number of times, you'll get a very massive tree, which won't save as many bits. And furthermore, every document will have its own different Huffman coding tree. It won't be like this all the time. It could be small, it could be larger. Now, to round everything off with compression, I introduced you to another type of compression called lossy compression. This is where quality is permanently removed or makes the file size much smaller. So think about like rounding, for example. For example, we could do this with the sound representation again. So let's say we have a wave. We can measure perhaps its height from a scale from 0 to, let's say, 100. At some point, perhaps, maybe here, there may come a point where it's between, let's say, 39 and let's say 38, and it just comes in between like this. We're going to have to round up or down, which makes it less accurate. Another way you could think about this lossy compression is if we literally use, let's say, 4 little levels to represent this wave. like the middle, the maximum, just little bits in between like this. What you then get is this almost more of a jagged wave when you're almost trying to trace it back. And if you get these jagged things, you'll notice that the file size, especially for sound, it will sound even much worse. And the one you're familiar with is lossless compression, so quality is removed, but it can be restored back later to its original one. So this is run-length encoding and Huffman coding, but it doesn't compress a file as much as lossy compression. Now next, we need to know about Boolean logic. So you may need to know and draw some gates as well as the truth tables. You need to know their symbols as well, because you could have expressions perhaps. So the four you need to know are these. Now, for example, the NOT gate is simply a triangle with a circle at the end. So for example, if your input is I and your output is Q, and we draw a little truth table, if our input is 0, it goes to 1, and if our input is 1, it goes to 0. So basically, NOT does the opposite. And that's represented by this symbol. The AND gate requires two inputs. It's drawn like almost a semicircle with one input out at the end. We'll label this Q again. We'll label the inputs A and B. Now, if I draw a truth table again, like this. Now, the output is only 1 if both are 1. So basically A and B are both 1. Or is similar to the AND gate, except this straight bit is almost replaced like a curved bit, almost becomes an arrowhead, and then it has one output at the end, Q, like this, almost. And it's probably best sometimes to label your gates like this. Now, if you draw the truth table again, now the output is 1 when at least one input is 1. And then finally, XOR is like an OR gate, except you have a line extra like this. Now this time the output is 1 when both inputs are different. So this is like when one of them is 0 and the other is 1. So 0 and 1, or 1 and 0. Now, a past exam question was to draw almost an XOR gate, made up of the other 3 gates, and or not. And this is a complicated one which you may need to know. So the output needs to be 1 when the inputs are different. So let's say we have our inputs A and B again. Now we can check the inputs are different, so we first get them through, like this, and then we let one of them branch out, almost, like this. It will go through a NOT gate. Now, when you're drawing some truth or logic gate circuits, and if the lines overlap like this, it's probably best to do a little curve like this. Then what you do is you feed them into an AND gate like this. And what this does here, checks if they are different. So it will take one of the inputs, change it to the opposite one, and then you'll combine it with the other with an AND statement. Now if that turns out true, that means the two inputs must have been different. So if we do an example, at this gate here, this receives the opposite of A, so not A, and B. So for example, if we do the truth table, if the inputs for example, if A0 and B0, so A would be flipped to 1, and B would stay as it is. That would output since 0 because neither of them are 1. Not both of them are 1. If we try, let's say 0, 1, B is 1, and we flip A, so we flip a 0 into a 1, so that becomes an output of 1, 1 and 0, weirdly, it flips A into a 0 and B 0, so this outputs 0 actually. And lastly, to check with, let's say 1, B is 1, A gets flipped from a 1 to a 0, checks if they're both 1s, they're not, so output 0. And this will basically happen in the opposite way for the other gate. It will invert B and put that in an AND statement with A. So this basically, those two AND gates checks if they are different. And then to finish it off, since sometimes, even though they're different, they can output 0, we have to put this through an OR gate. Then we get just Q at the end. Take a screenshot now. Now, other logic gates will have exam questions. For example, a laptop will sleep if not touched for 10 minutes and if it's not plugged in. So S is our output or outcome. And our inputs are like our conditions. And notice a few keywords like not, and, not, and so on. So we have our inputs T, so if it's touched, then P for plugged in. Now for both of them, you notice that there's not, so we put a not gate immediately. And then we need to let the laptop sleep if it's not been touched for 10 minutes and it's not plugged in. So we use an AND gate. We can move these in together slightly and just draw an AND gate. And then that's our output S. So for example, if it's not plugged in, that'll be a 0. If not touched, the not will turn it into 1 here. And since both inputs are 1, output is 1, so sleep. Next, you need to know about software. Now, you need to know about two types of software, which is application software, which helps a user to complete a task, and it may often have a GUI, which is a graphical user interface. Examples of this can be word processors and browsers, and remember, in an exam, you cannot name any brands. Now, the other type of software that you need to know is the system software, and this assists the computer system with managing and running the hardware. For examples could be security, OS operating systems. Security could be, let's say, antivirus. Now, you'll need to know about the operating system or the OS, and what it does, it handles the applications themselves, the CPU and memory, which you'll learn about in a later topic in this lesson, the interface, which is what's printed, and other devices that may be connected, things like headphones, speakers, mice, keyboards, and so on. These are often part of multiple choice questions, for example, to see the jobs the OS does not do. And you just need to know this. Now you need to know about types of programming languages. Now, here's some samples of programming code in different languages, Python and C++. And these do the same thing. Now, on the left, this is Python. On the right is C++. These can be technically both considered high-level languages, but as you can see, C++ looks a bit harder, if you like. For example, even when declaring a variable, you'll have to type the actual variable type it is. If you remember from the programming lesson, in this case, you had to define as an integer. Now, these do the same thing. They'll just um, declare some variables and print them out. Now, Python is said to be a higher level language compared to C++. And what this means is it's easier for humans to understand, but perhaps harder for machines. Now, why would we do this? Now, for high-level programming languages, as I've said, they're easier for us to understand, but they're harder for computers to understand. And one line of code is several for the machine code, and the code has to be translated to machine code or into assembly code by assemblers, compilers, translators, which you'll learn about. Whereas the lower level uh, code is more in the machine's understanding. It's easier for the machine to understand because, for example, assembly or machine code is literally binary or mnemonics. For example, one line of machine code is just one line of code for the computer, whereas let's say print involves a few different things. It will have to fetch some memory and do stuff with it before it's sent to a piece of hardware. Next, you need to learn about translators. So this is how, for example, the high-level programming code gets converted into the machine code or assembly code. First, we have assemblers, and these convert assembly code into machine code. And as you see on the right, this is high to low. This is like the language levels. So assembly code is often like mnemonics. For example, it will write some memory, delete some, move stuff to the right or left. And it basically a command. Now compilers involve the whole program. So the whole program is then translated into machine code and saved in another file and then executed. Now the good thing about this is if you want to test this multiple times, it can be faster. However, practically it's harder to find errors or to debug. This is because errors are displayed after the whole code is run. Lastly, you'll need to know about interpreters. Now, the program is also translated into machine code, but is done line by line and executed after. For example, it will look at the first line of code, translate it into machine code, do it, and then the next one. Now, it's slower because you have to decode and execute very slowly, but it's easy to find errors because at the moment when you find an error, it may halt or just stop. And often, for example, in Python, if you run some faulty code, it will tell you the line that it's on and perhaps tell you what's wrong with it. Let's say a missing bracket or colon or indent. Now, we need to know about storage, and it's a link to the CPU. Now, for the exam, you don't need to know about the CPU itself. You'll need to know what the fetch, decode, execute cycle is, and that's linked to the CPU directly. So this is what happens in the CPU when it handles instructions. So it fetches instructions from main area, decode, and then execute. Now, storage, the primary storage where it can keeps all these instructions can be, for example, RAM, random access memory, cache, registers, and ROM. Now, RAM is meant to be random access memory, so that's usually quite close to the CPU. Cache is even closer. Usually contains frequently stored instructions, because if it's closer, it will move along the buses, the ones that transport this information or instructions, and since it's closer to the CPU, it'll travel in a shorter amount of time. However, it tends to be more expensive. Now, registers are similar to cache, and they're even faster as well. And these are temporary instructions that are distributed, so registers will often receive other instructions from other places and keep them and then release them to the RAM or the CPU. Whereas the ROM loads the BIOS, and this is going to be compared in the next slide. Now, RAM and ROM. So RAM is volatile, meaning it um, only stores when the device has power. So when you turn it off, all memory is lost. Whereas ROM is non-volatile and doesn't lose memory. Another thing you could write about ROM is perhaps is it only read, whereas RAM it can be you can read and rewrite. So only things like the BIOS is stored here. So this is at startup. Now we got CPU storage and these are a few things you can consider to improve the CPU's performance or its overall um, benefits. The things we talked about were RAM versus cache and the registers as well. Now, cache could be used over the RAM because I said it was closer to the CPU and it stores the most frequent instructions, so it doesn't have to travel a longer distance several times from the storage to the CPU to be decoded and executed. However, the size of storage, cache is much smaller, and usually because it costs more per storage or unit of storage, like megabytes. Now, secondary storage is what many people think about storage when they, for example, buy a new phone, transport files over the internet or in pen drives. Now, there are three types of secondary storage you need to know. First one is the hard disk. This is a magnetic disk. and how this is read or write. So what happens is it spins around. Now, to read the magnetic disc, there is a reading arm, and it hovers above the disc. What it does, it detects the polarity of the disc section. For example, that's if it's north or south. And that determines if it's a 0 or a 1. Whereas to write, it's similar. A writing hovers and then can change the polarity of a part, the disc. Now, solid state drive is slightly different. I don't think you need to know how it's read, but it's rather just a simple electronic circuit. What it is you'll have several little pits here. And this can be filled or not filled with electrons. And this can determine if it's a 0 or 1 that's shown in each pit. Now the optic disc happens to be very similar to the solid state drive, except again it's a physical material, and this time, if you've heard from your parents, the disc is burnt. So to read the disc, what happens is you got the normal surface of the disc, but what can happen is you can have a laser to write. What it can do, for example, it can put a few indents like this called pits. What these do is when we read them, the reading arm hovers and then emits light. Now, it's not reflected. That's if there is pit, and it's reflected if no pit, like not burnt. This is called land, and it's often made up of a reflective material. That's why you see many discs shiny. Whereas to write, the writing arm also hovers, but then uses a laser to burn some into pits. This can represent 0 or 1. You'll also need to compare all three of these secondary storage forms together. Now, there's a few ways to think about each, like for the performance. Usually, you could think about the price per unit of storage. That could be, let's say, per gigabyte, its reliability or lifespan, the read-write speeds, or the portability. These would often be like 9 to 12 mark questions. Now, we're going to compare each. Let's say we'll have optical, we have solid state, so SSD, then we have magnetic, so hard disk. Now, firstly, overall, optical disks are the cheapest, while SSDs are the most expensive. So we could possibly like rank them, so 1, 2, and 3, best or worst. However, optical disks tend to be the lowest capacity. They can't really store much. Whereas magnetic disks can store a lot more. You can also see in many new laptops solid state drive memory, whereas the old ones would tend to have magnetic drives. Now with the reliability or lifespan, this refers to, for example, if it can get damaged easily. Magnetic hard disks can easily get damaged. Same with optical, so I'd say they're equally the worst. So this would be so optical, it would be like scratches, that's like CDs. Whereas with magnetic ones, it can be via impacts, like being dropped, other magnetic fields as well. Whereas SSDs would be the best. They rarely get damaged. However, with lifespan, SSDs start to run out a bit, or they start to degrade. Whereas opticals, I'm not sure. Whereas magnetic often stays magnetic for a long time. So the reason why the SSD degrades is because when you rewrite the memory, like when you remove or keep filling electrons, that starts to wear off the actual memory where it's stored, like the pits of where electrons can be stored. In terms of read or writing speeds, SSDs tend to be the fastest. Next is magnetic, whereas optical is the slowest. And even worse, most CDs or opticals can only be written once. In terms of portability, SSDs are the best usually because you have pen drives. Opticals tend to be next. You can easily carry disks, whereas magnetic drives, they tend to be large and bulky. And usually at the end of with a question, write a conclusion. Next, you'll need to know about cloud storage. So this is where um, files or other data can be stored on external servers that's run by other companies, usually by the internet. Now, this can be also another high mark question, which could be, let's say, 6 marks, and we discuss the benefits and drawbacks. Now, I'm just going to do it simply, draw a little table. Now, one obvious benefit you could point out is that you don't need servers yourself, so save money with, let's say, equipment like the servers or the rooms that you need, as well as the people needed to maintain it. You could argue as well that many services offer some memory for free. Another benefit is as well, since it's over the internet, it can be shared easily. So this could be good for, let's say, offices. In this context, could be said in the question, for example, why could an office use the cloud storage? Now, the drawbacks, however, there are quite a few. And this can get expensive quickly because you've got other servers doing what you should have been doing, and they will have often very large, like warehouses, for example, of these servers, and often you'd pay like some sort of monthly fee. Next, you could perhaps question the security of the data. You could also question who's using the data, what for. Some other ones could be, for example, as I said in the question, you'll need internet connections. That can be either from home, the office. These can be expensive for some, or even not even available to some, depending on their location. With security of data, you could link that to a later unit with hackers. And possibly the GDPR as well. Next, you'll need to know about networks. So this is an entire new unit. So a network is a system or a network of computers, so multiple computers. This is to share files and resources. This is ideal, for example, in a school. Instead of having a printer in every single classroom attached to their own computer, each department, for example, could share a larger printer, because often the printers that are in each classroom aren't being used all the time, and they could easily be shared with others. Networks allow this to happen. Networks can also act a bit like cloud storage. So anywhere else on the network, for example, you could be in another part of school, you could access files or your own designated area files. Now, this in itself can be a discussed question again. Why use a network? Why not? I've discussed some of the benefits for our example. Now, some drawbacks could include, for example, the security again. For example, things can go wrong, let's say, with misconfigured access rights. Some people having access to files they shouldn't. You could have unauthorized users on the network. You could also have other cybersecurity threats like malware that can spread easily because everything is connected together. These networks can also be difficult to manage in terms of, let's say, actual equipment and staff. And often these are sometimes have a question of reliability. These networks often depend on a few servers. Next, you'll need to know about these cybersecurity threats. So these were under the drawbacks of having a computer network. So this can be the disadvantage. Now, there are different threats. First of all, you've got malware, in which of them you've got different kinds, such as Trojan horses, viruses, and worms. Now, the Trojan horses try and disguise themselves as, let's say, innocent files, perhaps, and then they get in, and that's when they cause damage to computers, can spread around, and so on. Viruses are simply infected on their own. They'll just infect your system whenever you open it, and it can then perhaps um, get spread to others. For example, that could even by email through networks and so on. worms, and they will often embed themselves deep into the computer and then also spread like viruses. Now, if there's a few ways to actually reduce these threats, for example, malware. This can be by reducing how they get in. That's through, let's say, phishing, unauthorized access, and these are also, some of these are called social engineering. Like, for example, blagging is making up fake stories which persuade you to do something you shouldn't. Eavesdropping is simply um, listening to, let's say, radio waves on the Wi-Fi level. Could be also listening to passwords, or same with shouldering. You could also prevent the spread of malware by preventing from circulating via the network. For example, you shouldn't open suspicious files by people you don't know. You shouldn't as well insert random things like USB sticks and so on. Now, one way to protect networks could be through encryption. So encryption is where we convert plain text to or back to ciphertext. And we want only the plain text for those, for you and the person you want to send it to. So then first it will be encrypted, going from plain text to ciphertext, whereas it will be decrypted when from ciphertext to plain text. Now, symmetric and asymmetric encryption will do these differently. So symmetric will often use the same, what we call a key. What this means is, for example, if you used symmetric encryption over the internet, what you'd have to do is send your encrypted message and then send the key separately. Now that's very risky because it can easily happen where your encrypted message can be intercepted as well as your key, so anyone else could easily decrypt it. And also another disadvantage could be these are weaker because they can be broken by brute force. Whereas asymmetric encryption uses two keys, a private one and a public one. Now the public one is used for anyone else that wants to communicate to you or send messages to you. Whereas your private key must be kept private because this is the key that you use for you decrypt. Another way you can protect networks are through firewalls. So what these do if I draw a little mini wall, what they do is they often stop unexpected traffic, like internet traffic, coming into and out of the network. An example can be from suspicious websites. Next, another way you could use is MAC address filtering. So the MAC address is a unique identifier for hardware. And whitelisting will only allow specific MAC addresses, while white blacklisting will ban specific MAC addresses. Now, some other ways you could protect networks could be through authentication. There are three ways of not authentication, something you know. So these are often passwords. These could also be like pins, answers to secret questions, and so on. Something you have. This could be, let's say, some verification code. So these are the ones sent by text. Could be some, let's say, physical objects, like lanyards. Something you are. These would often be biometrics. This would be like face recognition, fingerprints, and so on. And it's probably best to have at least two of these. This is called two-factor authentication. The last one is CAPTCHA. So this is completely automated Turing complete test. So it underlines all those capital letters CAPT. C, H, and A capture. So this basically can block like bots, like the spam, let's say for websites. And these are often things like where you click certain pictures or type in a bit of text. But sometimes these machines can actually be quite good, and that's why they make new iterations of capture 1, 2, and so on. Unless there's user access levels, so these will authorize like this intended users to access files or just a network itself. Now, moving on to the networks themselves, you'll need to consider three types: PANs, LANs, and WANs. So PANs are personal size, and these are the smallest, and these cover, well, they don't need much needed. An example of this would be Bluetooth. These connect some devices. LANs are local, and then they span like the just one geographical location. Such as a school. And there is equipment needed, but equipment is owned by the organization. And it connects many various devices. And lastly, the WANs are wide area. So these are multiple sites. The internet itself is a WAN, whereas the equipment owned by companies. These can be, for example, internet service providers. And these also connect many devices. Now, how can devices be connected in networks? Well, one way can be using wires. This can be using, let's say, coaxial, Ethernet, or fiber optic. Now, these can be used over some other methods like wireless ones because they tend to have a higher bandwidth. So like that's how fast data will travel. And these tend to be consistent as well. And good thing is that these is consistent because the wires So the wires can transmit data over longer distances. So the other method, as I've said, is the wireless one. So that'll be often, let's say, Wi-Fi. Now, you would probably use this over wired ones because wired, they need expensive equipment. That's like the wires themselves. They use copper, so technically wireless is actually better for the environment. So those for both were benefits. Now the drawbacks, these were like here. So like the wide ones, they can be quite expensive, like especially if like your LAN itself is a large area. For the wireless, it's a lower bandwidth. Less consistent. This is because if you move away further, and there's any obstructions, you get a lower bandwidth. Now next, if the PowerPoint doesn't lag again, is the network topology. So you have the bus and the star. So this is how many of these computers can actually be connected together. So a bus is like one line, if you like. So you'll have a terminator at each end, and each, let's say, box, like a rectangle, is going to be a device or a node. Now, what you'll have is your cable from the two terminators. Usually at the center, you'll have your server, and then you'll have ones branching out just like this, just nearby, with all the devices. One's just like this. Now, the problem is, it's dependent on this wire. If it fails, whole network does. However, you do use less wire. But since, however, all these computers connected to the same wire, there are many collisions. That's when data is sent over a network, which you'll see in the protocols. So like many data is lost as well. Whereas the star, you'll have the switch at the middle, and then it will just branch out to all the devices. So if one wire fails, only part of the network fails. You could argue this as well. It's easier to and maintain. However, you do use more wire. Now next you'll need to know about protocols. Now what's meant by a protocol? So these are a set of rules for which how devices communicate in a network. Let's say that could even be over the whole internet. Now we have the layer model represented by a table. So layer 4 at the top has the application layer. Next, layer 3 that has the transport layer. Next, layer 2 has the internet layer. And then layer 1 has the link layer. So what these layers do is they do a very similar job without worrying what happens in the other layers. So data will get sent up or down each layer like this. Now the protocols, let's say at the application layer, will include, let's say, websites. So that'll be like HTTP, HTTPS. That's for viewing website files onto your screen. You can also have FTP, which is like File Transfer Protocol, SMTP, IMAP. So those are like messaging protocol to send messages. At the transport layer, you'll have TCP and UDP, which are how packet switching occurs and how they get sent. Internet is IP, so that's where you have your addresses as well. And then you'll have each packet going down the quietest route. And the link layer is like your actual network. So this is like your Ethernet, Wi-Fi, so on. Now, we're going to go through each of the protocol layers. So, application. So, HTTPS, this is for viewing website files. And HTTPS is just the secure version. This is often by encryption. The asymmetric version, which is also called end-to-end encryption. One other thing you could have is FTP, which is file transfer protocol. Another one you could have is IMAP, internet messaging. So an SMTP is just used to send emails. And if you remember, the applications, such as application software, these will often get the user to interact. And what you don't want with the layer system is that the people at the application layer not having to worry about what happens, let's say, at transport, the next layer. This is where packet switching occurs with these two protocols. So what happens is, um, data is split into like smaller chunks, because when you send it over the internet, it might get lost, and it's not good to send it all in one big chunk, because if it gets lost, for example, it doesn't end up to the recipient, you'll have to send it again, possibly again. So we split it into smaller chunks, so smaller chunks will only get lost. So these are called packets. Now, so with TCP, so the packets are labeled like with their order. It's like when they should be assembled. As UDP, packets aren't labeled. They're just sent as they are. Missing packets aren't checked for here. The next two layers are layers 2 and 1. So layers 2 is the internet. So this links into the packet switching with the IP addresses. So each packet is labeled with the sender's IP address and then the receiver's IP address. Now this is responsible for the packet switching itself. So this is where each packet is sent down the quietest route to minimize like collisions or packet losses. The final layer you'll need to know about is the link layer. So this involves the actual hardware and topology. Now, suggest which topology might be better now and why. I would argue it's a star, because you have separate wires from the node or device all the way to the switch. So this minimizes packet loss. So things are received now. The last section of tonight is is the ethical issues. So you need to know about some computer legislation. So the first is the Computer Misuse Act, and here are a few clauses which I copied from the government website. And the first says the unauthorized access to computer material, so that means access to things you shouldn't have. Second is the basically using computers to commit other offences. Number 3 is to basically break a computer. 3ZA is the same again. And 3A is basically helping anyone else who commits the Computer Misuse Act or breaks it. Now, some of these will basically or make so, for example, this would make hackers' actions illegal because, for example, they get hold of information or computer material like your own computer without you knowing, without your consent, for example. That's what it's meant by unauthorized. The next is the GDPR, so that's the General Data Protection Regulation. So data should be used fairly, lawfully, and transparently. So basically that means you should be told what the data is used for. And only that necessarily, not anything else. And it's accurate and up to date. So the data needs to be accurate and up to date, as in, like, for example, if you move house, you may need to tell certain organizations that you've moved house, so it's accurate. So it's only kept for no longer than necessary. For example, schools keep data for 25 years, maybe even more. And lastly, it's handled security, especially when perhaps disposing. So that's like, for example, deleting, shredding, etc. Not, for example, via general waste. Because this can lead to all this, especially this, this. That's when you get hand of data you shouldn't have access to. Now, other legal issues could include, let's say, copyright and patents. So this is a link to, let's say, other things like inventions. So copyright is where there's automatic protection to someone's work, and patents are basically they protect the function of something, how something works. Now, those laws are often broken through piracy and cracked software, for example. So these are illegal copies, often free. And rightly so. For example, these copies shouldn't have been sold because, well, it takes money to develop all these various softwares, and to license them out is probably quite expensive. On the other hand, you have other things like copyleft and fair use. Fair use is something you may see on social media or YouTube. For example, you will often see many videos using songs without, for example, explicit permission from the actual songwriters or corporations. But not letting them use it is another issue in itself. That's why you have things like content ID claims, because sometimes it's hard to get hold of these permissions for the right of like these copyright holders. You've other legal issues could be responsibility. For example, can automated machines or robots be accountable legally when breaking laws like humans? For example, with murder, with the two train tracks problem, can they make those some other point to consider? Those are common points, let's say, against the use of automated things like self-driving cars. Now, we'll discuss quite a few ethical issues, and the first one we'll look at is hacking. Now, which law does this break? This is the Computer Misuse Act. And how can this happen? Now, for example, this can happen in networks, social engineering. There's something to consider is anything connected to the internet, because that is actually a big network. It can be accessed by anyone, and it's quite vulnerable. Now, hacking can actually be useful through penetration testing. So you have two types, white box and black box. So this is where we test the like cybersecurity measures or how good, for example, the staff are, let's say, in a company or an office to prevent, for example, viruses getting in or hackers getting in. So white box is where some information is given, while black box, no information is given. For example, the hacker will have to try and, for example, obtain it. Another ethical issue we're looking at is data access or privacy. So here's a situation now. Someone you have contact with, let's say by email or phone, is accused of being radicalized, let's say, like in a terrorism way. So that means they're a threat to the public. Now you and others that are connected to this person are being investigated by the police. You think you're innocent, but should the police have access to your communications as well as others? Now, firstly, here are some points against this. For example, data is already encrypted asymmetrically or end to end, so how could they access this? Well, obviously they could by your phone itself. Could the police access data without you knowing? These are what meant by backdoors to encryption. So like these are secret ways organizations like the government or police can access encrypted data. But the problem is if the government can see the data, who else can or even gain access to? You could argue the data can be misused as well. This links to the GDPR. For example, what it's used for, how long, to who, because they might even search your contact as well. Whereas some benefits, or people would agree with this because it's for the greater good of society, they see the risk of criminals perhaps outweighs. You can prevent incidents in the future, perhaps. And there's the argument of nothing to hide. The third issue is the environment. So a link to other subjects can be life cycle assessments. So firstly, whenever new devices are made, raw materials are needed. So these are often very special metals, and these often have a finite supply. So if we make more phones, we'll use up more of the metals, and this finite supply of metals will run out faster. You could also have other metals such as copper. Now, next, after you get the materials, you'll need energy or electricity to manufacture it. You'll then have other things when you use the device itself. Again, electricity. For example, how much is needed? That's like your power rating. Problem is that some electronics need to be on all the time, such as servers at schools. And at disposal, some materials can't be recycled, but they could be separated. So we can, for example, cycle those special materials or special metals. And finally, as a result, since the things that can't be recycled, these e-waste products can then be transferred elsewhere. And a good case study you could do is Agubloshi, where that's a common site where e-waste is disposed of from other countries. And one thing you may want to note down is some new legislation. And so this basically controls basically pushes And finally, we'll go through some SQL. So this, ironically, is some more programming. Now, we've got this table here. Now, what does this command return? So first of all, select speed is what we want, and this star means all records. or actually all fields. So that would be like your ID number, name, country, age, gift wanted, behavior, and so on. Now, from is like the table. We'll label this contacts. And then where is a condition. And often you'd have something very similar to Python, where you'd have a string and then an equals. Though this time you only need one equals to compare. So overall, an SQL query, so select any fields. You can have any individual fields, like multiple of them, but they all have to be separated by a comma. And then from, you'll have to specify the table. And then where, so that's like a condition. And then often you could have a sort by, like any, let's say, variable ascending or descending. So what this ultimately does, this command here, it'll select all the fields, ID, name, country, age, gift wanted, and behavior, where the behavior is nice. For example, this, and this. So for example, it would return ID 1, this could return, for example, this, this. So it'll return all the fields, as I've said, only if it says nice in the behavior column, whereas everything else isn't. Now, another SQL statement you could try is to now delete all the details of the naughty records. Now, records are these rows instead. So these are like the IDs. So each person. Now, to delete, you start with the command delete. And since you want to delete all details, so that's all the fields from the table contacts, where behavior naughty. So this would get these ID 4, 2, 4, and 5, and basically just remove them from the table entirely. And lastly for tonight, our relational databases. So that's where we have two or more tables. So Santa then hires distributors to deliver these gifts. So each country has a specific distributor which can be shared by others. So write an SQL command that returns the child's name and the distributor they're expecting. And basically here there's no other really for nice or naughty. And the second table is here, so we'll call this distributors. So this is going to be a query again. So first we start with select. What we're going to select is the child's name, so that will be the name. However, you have to specify the table that it's from, so that's the contacts. And have another field, which is the distributor. That will be from the two tables, contacts, distributors. And you essentially want to match the country here to what the child has. And you do that by the country that's in the contacts is equal to the country in the distributors. And this would be, for example, let's say with this guy, Nakamura, he's from Japan. So he would actually expect DHL to deliver. So it would return his name and then the distributor he's expecting, DHL. Now that's actually it for now. That was quite a long lesson. I'll see you soon.